Good afternoon. Today we'll be presenting our final thesis presentation. Our topic is controlling holograms using real-time gestures. At first, let me thank our advisors, Dr. Goneid and Dr. Khalil, for their constant support and motivation. And then let me first start by introducing our team. First, Mark, the most demanding team leader yet. We made it because of him. Second, Michael, our genius and definitely our lifesaver. Third, Zeyad, the one who's always optimistic to an extent that he oversimplifies everything. Sherry, the one who keeps all her anger inside and still manages to stay our positive vibe. And finally, me, the tiniest member of the group, but has a huge role in keeping us all together. I'll start by guiding you through our outline. First, I'll start by talking about the problem versus the solution, or in other words, explaining our product and its capabilities. Second, I'll talk about the progress since last presentation, or what we have reached since the last demo. Third, we will talk about explain the process and its output. And finally, we'll talk about what we reached or how we reached our goal in the final product. Okay. Let me start by addressing the problem that is in hand, or in other words, what made us choose this project. We noticed that there was a full dependency on devices to manipulate any sort of model through the mouse and the keyboard. In addition to that, motion detectors are expensive, so a camera would be a good alternative. And that with the advancement of technology, such remote manipulation using external devices and add-ons will be a part of everyday life instead of a normal keyboard or a mouse. We also found that their models are deployed on the holograms as a 2D display, and they need adjustment before being deployed. Okay, so what makes us special or different? People have been impressed by hologram projection, as it gives the illusion of a virtual 3D model in real life, manipulated using controllers. There has also been another technology of giving commands to the computer in a 2D scale, using gestures. What we've done is created the possibility of controlling any model on a hologram device using gestures with the aid of a webcam. First, we managed to detect motion with the use of without the use of any additional sensors or motion detectors, and we've only used a very simple webcam. Second, we created our own hologram deployable model using 3GS, and therefore we won't need any external designer or tool. And Michael will elaborate more about 3GS. Finally, we're planning to create our own holograms or collaborate with local manufacturers to reduce the cost as much as possible. Now I'll talk about our progress since last presentation, which will be further explained by my colleagues. Okay, so we enhanced our desktop application. We added inertia in 3GS. We also implemented zoom in and out using gradient orientation. And finally, we implemented a CNN model to classify the 6 gestures. And Michael will talk more about 3GS.
Okay, so now if we think abstractly about a project, we can divide it into 2 main parts, the gesture recognition system and the model holographic deployment. We'll first start with deploying our 3D models into this hologram, the DreamArc HD3. For those of you who haven't seen this, the hologram, this is how it looks. Okay, so 3GS, the brain of our deployment system. With the help of 3GS, we were able to deploy 3D models on our showcasing device. We won't go over what we did with it in details, but we'll just highlight the most important features that we implemented in our system. First, auto-scaling. 3D models different in sizes, some are big, some are small. So we implemented an auto-scaling mechanism to accommodate the different sizes and well position the model in its right place. Secondly, mirroring, of course, or the duplication. The duplication of the model 3 times with different angles and different rotations to be able to view the model from any of the holograms 3 sides is generic enough to be applied in the same manner to any applicable model. It's also not exclusive for the type of the hologram we're using. For example, if the hologram had 4 sides instead of 3, with a back view, for example, with few modifications, the same algorithm can be applied to achieve the same results. Finally, the type or the format of the models. Currently, the accepted 3D formats are .glb formats, but this is not the end of it, as more formats can be incorporated, also using similar mechanisms, but with few modifications. Okay. So this is just a refresher of how the model looks like after it's processed, and this is what is going to be deployed on the hologram. And later you will see how this falls into the hologram's prism. Okay. To show an example of what we additionally implemented since our last presentation, in the GIF on the left, this is a 3D model rotating to the left. It's clear that the way it rotates seems a bit unnatural, as if it's lagging. However, the updated one on the right, its rotation seems more natural. We've implemented an inertia-like feature so that the model appears to the user as if it abides by the rules of physics, and thus making it more realistic for the user. And now Zeyad will move on to the second part, the gesture recognition system.
Gesture classification was one of the most important problems we had to tackle during our project. One approach we attempted was to classify each gesture using machine learning. To begin working with machine learning, we first had to construct a viable dataset. Each of us filmed ourselves performing each gesture hundreds of times, then ran our MHI algorithm on each video to transform them into several individual frames. We then labeled each frame, and by the time our dataset was complete, it had a total of 5,455 samples. We could now begin training in earnest. Next slide, please. In choosing our model, we eventually decided on using a convolutional neural network, a CNN. A CNN is a deep feed-forward artificial neural network. They are generally used for image classification, object detection, face recognition, and even with self-driving cars. The CNN works by defining several convolutional layers. Each layer computes the output of neurons that are connected to local regions of the input, each computing a dot product between their weights and the input field. Each computation leads to the extraction of a feature map from the input frame. The next step is max pooling, a technique where we select the highest pixel value from a region depending on its size. This gets us an input representation by reducing its dimensions and reducing overfitting. This all leads to the fully connected layer. The objective of this layer is to flatten the high-level features that are learned by the convolutional layers and combining all the features together. It passes the flattened output to the output layer, where a softmax classifier can predict the input label. The results were quite promising. After testing with several different parameters, we managed to achieve a very high accuracy when we ran our model on a small testing dataset. Our next step was to see how the model functioned in real time and compare that with our gradient orientation results. We tested both models in good and bad lighting and began calculating accuracies. With the CNN, good lighting achieved accuracies ranging from 79% up to 93%, while bad lighting achieved accuracies of 74 to 91%. Originally, we implemented a method using computer vision techniques instead of machine learning, specifically the gradient orientation technique. After testing gradient orientation using the same testing parameters, good lighting achieved accuracies of 82 to 98% for each direction, while in bad lighting, it achieved 70 to 80%.
Okay, so summarizing what Zeyad said, this is the conclusion of the comparison. With good lighting, the gradient orientation approach achieved better results with an average success rate of recognizing a gesture and reaching 94%, while it's 86% for the case of the convolutional neural networks. In the case of bad lighting will mean a direct light to the camera. Both approaches achieve similar results with around 84% accuracy. In terms of speed, however, the CNNs is slightly faster with an average time of recognizing a single gesture of 112 milliseconds. These numbers are good indicators of which approach we decided to take. But still, both approaches are very prominent, and each one has its own advantages. Neural networks, of course, are scalable. Perhaps with more data set, it would perform much better. For the gradient orientation, it has a big advantage of not limiting the user to a specific gesture, meaning that you could, for example, make a swipe right with an open fist, a closed fist with any of the two hands, with your palm facing inwards, outwards, sideways, possibly anything. This also gives a degree of freedom to the user and makes it even more a more natural way of making gestures. And now Sherry will talk about our final decision.
Now that we've compared between gradient orientation and convolutional neural network, we can conclude that the gradient orientation method is the one we're following. Even though we're taking this path, the machine learning technique may prove to be more efficient and overcome the advantages of the gradient orientation system if there was a larger and varied data set. We have 6 gestures: up, down, right, left, zoom in, and zoom out. We don't need any sensors. Only the camera is enough to capture the motion and send it to the model to behave accordingly. There are some limitations, however, to the usage, such as light variations and background noise that might affect the transition of the gesture to the model. The last feature is that we can perform the gestures using both hands. For example, I can signal the right direction by either my right or left hand. Moving on to the system overview, the gesture recognition system can be narrowed down to the following. We started by subtracting the background using the Gaussian mixture model to avoid any noise and separate the background from the foreground. Then implemented the motion history image to follow the motion gradually, followed by structural similarity rate to compare the frames generated with a black frame to see if it's worth considering as a gesture or not, and finishing with the gradient orientation that allows to virtually create arrows pointing at the most recent motion. As for the model deployment system, we used Three.js that Michael talked about earlier. Together, we have ourselves a product. According to the user's point of view, we've done some adjustments to the desktop application that is accessible to the user. This was the very first design. Then we moved on to this one, and this is the final design.
Now we have concluded that the input will be consisting of a model, a gesture out of 6 that can be expanded later. The process is what my colleague Sherry have just explained. And finally, we can see the hologram executing the gesture smoothly. As you can see, this is the desktop app. Can you next, please? As you can see, this is the desktop app with the hologram. Desktop application has 2 main primary functions. First, detecting the user's gesture using the webcam. Second, rendering the model on the hologram. Instead of me taking a lot of time discussing and explaining how it works, let us show you what we have accomplished through a year of hard work through the demo. So this is how I'm gonna add the model to the application. This is how we inserted the model. This is us presenting to you how the hologram itself looks like. This is us taking a video of it from the 3 different angles, 2 sides and the front. The video may be laggy from your side, but the diagram is moving smoothly through the hologram. As you can see from this image, the background has the average lighting of a room. The background is considered to be complicated. As you can see, there are some white and red in the background, and it's not easy to detect it. However, it's working fine. This is us doing different gestures, zoom in and zoom out, swiping up and down and left. You can see in the monitor of the laptop that's showing, this is the motion gradient showing the direction where it's going to move. Later on, we're going to change this to show the one who is presenting the view, but just we wanted to show this as a type of illustration. So why would someone purchase our product? First, for simplicity. As you have just witnessed, with a simple GUI in few steps, our product is easy to understand and use without any confusing instructions. It's affordable. I'll break this down furthermore in the next slide. Our main product is an application that can detect gestures and have the ability to fit models on a hologram. Each task can be separated from the other, not forcing regular users to purchase a huge hologram to use the gesture detection part. In addition, it's unique. The uniqueness lies in the concept of using a hologram that will give a huge edge to companies, where they will brand themselves as modern and tech savvy. As mentioned previously, next. As mentioned previously, we decided that our thesis project is best suited for a business project. With that being said, here is our business model canvas. Since the manufacturers of our hologram are slightly expensive, we plan to team up with local hologram manufacturers and 3D model developers. We'll be able to grow in the market and sell our app. The main costs will issue from the app development, which we are currently working on, and the research and development team, which will be working on the hardware itself. The cost of the hologram and the marketing team. As for the revenue stream, we'll be able to sell our app to marketing, construction, and other firms. In order to ensure good customer relation, we'll try to team up with websites like Sketchfab that have different 3D models. And when the customer gets a model through our app, we'll get a commission from it. Thank you for listening. Do you have any questions?